Hi everybody, welcome to another Astronomy 102 lecture. In the last lecture, Maria talked about the death of stars, and in this lecture we're going to come full circle and talk about the very beginnings of a star's life. The process of star formation is also a process of planet formation, so I'll finally get to talk a bit about planets here too. To give you a sense for what we're going to talk about today, here's an outline on the right in words, and on the left, a pictorial outline of what I'm going to talk about. So I'm going to start by talking about how stars are born in regions of the galaxy called giant molecular clouds. Then I'm going to talk about how stars form through gravitational collapse. And I'm going to talk a little bit about what happens to the material surrounding them, which takes the form of disks and outflows and remnants of star formation. And the material that surrounds stars as they're born is actually the material that is incorporated into planets. So I'll talk a bit about planet formation. And then I'll wrap up by talking about the interstellar medium, the material between stars, and nebulae. And then just a little bit about supernovae and star birth. So here's the first picture in our vision of what it takes to form a star. So in the galaxy, there are regions of dust called molecular clouds, gas and dust called molecular clouds, or star-forming regions. And they're called molecular clouds because if we take spectra of these regions, we actually see emission lines of molecules. So here's an example spectrum of a molecular cloud that shows a whole wealth of molecules present in that cloud. So the reason that molecules are able to form in these clouds are because they're very cold. You don't create molecules in very hot regions like in stars. So we don't ever see molecules except in the very coolest of stars. And in these molecular clouds, which are very, very cool, we see lots of molecules formed. In fact, we've seen molecules up to 12 atoms, so you can form actually fairly complex molecules. Here's just a table that shows a bunch of the molecules that were detected in molecular clouds, and this was compiled, 14 years ago now, in 2000. So even in the year 2000, we had detected many, many different types of molecules in molecular clouds. So they're very interesting regions. And here's just a picture of one. So an example of a giant molecular cloud here, a region called a Bok globule. And you see it actually as a patch of darkness. So it's not something that glows like stars do in visible light. In fact, if we want to see into a molecular cloud, we generally have to go to longer wavelengths. So for example, if we looked at this Bok globule with a radio dish and we took a picture of it at radio wavelengths, what we would see is something more like this. So Bok globules, giant molecular clouds, they emit radio wavelengths. And if you had looked closely at that spectrum on the last page that I showed you, you may have noticed that those were very, very long wavelengths. So when we look at these giant molecular clouds and we take spectra of them, we look for the molecules that they contain, we're looking in the radio in general. And what makes it dark is dust. So there's dust present in these giant molecular clouds, and it's what absorbs visible light and makes it dark. So before I go any more into that, I'd just like to tell you a little bit about what I mean by dust, because I think when we hear that word, we think of household dust, which is actually very different from interstellar dust. The composition of household dust, I hate to tell you, but it's true, is mostly dead skin cells, the poop of dust mites that live in your furniture, and fibers from your clothing. And when I say dust between the stars, obviously that's not what I mean. Interstellar dust grains are just solids. They're anything that's a solid and not a gas we call dust. So interstellar dust grains are the material that's between stars, and interplanetary dust grains which are a little bit bigger, are the material in between planets, so surrounding stars in sort of planetary systems. And if you want to see evidence that such dust exists, you can actually see it with your naked eye. All you need to do is look up in the sky at the Milky Way, and you can see that it's not completely bright. There's a dark patch that runs through the very center of the Milky Way. And we know, because the Milky Way is the plane of our galaxy, that there's lots and lots of material there, so why should it appear dark? It appears dark because our galaxy is permeated with these giant molecular clouds with regions that are dark and cold and dense and composed of dust that's absorbing visible light that's emitted elsewhere in the Milky Way. So at the very center of the Milky Way, you actually see large patches of dust. But just because these dust patches are opaque to visible light doesn't mean that we can't find anything out about them, because I said before, they were transparent to radio light, they emit radio light, and they're also transparent to infrared light. So on the left here you see an image of that same Bach globule in visible light, and on the right you see what it looks like in the infrared. And what you're seeing there in red are all of these background stars behind the Bach globule, so we can see through it in the infrared. These clouds also evolve with time. So they go from being black to glowing red. And what causes them, so here's an example, this is the Orion Nebula. And this transition from a dark nebula to this glowing red, what we call H2 region, which I'll talk about a bit later, is the formation of stars. So unlike the Bach globule, here again we have the Orion Nebula in visible light on the left and in infrared light on the right. But the stars that we're seeing here, these very bright stars in the infrared, and we can see through all the dust and gas, those are newly formed stars at the very center of the Orion Nebula. So star formation doesn't happen everywhere at once. If we look at other regions in the Orion Nebula, you can still see dark patches like this one. This is called the Horsehead Nebula because it looks like a horse's head. And what you're seeing is actually a patch of, you see this glowing background, red background of the H2 region of the Orion Nebula. And in the foreground, there's this patch of dust that hasn't quite collapsed to form a star yet. And it may actually dissipate before it gets a chance. So the takeaway here is that molecular clouds are patchy. They're not a uniform density. So for various reasons, some areas are denser than others. And all you need to form a star is for a patch in this molecular cloud to be dense enough to collapse. So the second step in the process of star formation is gravitational collapse. So you have a dense molecular cloud, you have a region of dark, cold, dense gas and dust, and if you can cause it to somehow collapse, which can happen for a variety of reasons, I'll give you one towards the end of this lecture, you can start to form a star. So if you can make a region that's dense enough, and you call this region a core, if you can make a region that's dense enough to start to collapse under its own gravity, it will eventually collapse far enough to become a star, but it's kind of a long process. So as the core collapses, energy increases because of the collapse, this energy of collapse, but some of it will be able to escape via radiation. So you'll start to heat it up as you collapse, and it will start to radiate. So gravity is winning in these cores, but it's doing so really slowly because as they collapse, they start to radiate and generate energy. And so that slows the process of gravitational collapse. So contraction of one of these cores to form a star is very slow. And at the point when it starts to collapse and radiate, when the collapse is sort of inevitable, it's going to collapse to form a star, although it's going to take a while, we call this a protostar. And the energy source for a protostar is the collapse. It's not fusion, and that's why we don't call it a star, but a protostar. And I said that the the force of gravity collapsing this material is slowly winning, right? It's collapsing under gravity. It has too much mass and not enough outward pressure. So it's not in hydrostatic equilibrium. But it's a slow collapse because lots of energy is being radiated in the process, so gravity wins very slowly. But what happens to the materials surrounding the star? Only the very core of this cloud has collapsed to become a protostar. So what happens to the rest of the material around there? So let's add another picture here. In this protostar phase, in the picture on the very right, you'll notice that there's not just the protostar at the center, but now there's all kinds of stuff that's going on here. So when the cloud was in the sort of dense molecular cloud phase, it was spinning very slowly, and as it started to collapse, that increased the speed of rotation for the same reason that when a figure skater pulls in her arms, she starts to spin faster. A phenomenon called conservation of angular momentum. So the material that's pretty far away from the protostar, it's not very affected because it's not collapsing very much. But as you get closer, the material, as it's collapsing, will start to spin faster and faster. And here's where another thing comes in. And I think the easiest analogy to imagine why this happens is to think about someone throwing pizza dough in the air. So why do you throw pizza dough in the air? You do it to spin out the crust and make it thin and big. So if you take a small flat disk of pizza dough and you throw it in the air, it'll tend to, as it spins, flatten out and thin. And that's exactly what happens around a protostar. The material, as it spins faster and faster, will tend to collapse to form a pancake or pizza dough-like disk of material that we call a circumstellar disk. But a theory like this, so this theory of star formation, that we go from molecular cloud to gravitationally collapsing core to a protostar with a circumstellar disk, theories like this are only as good as their predictions. So to validate this theory of star formation, we need a testable prediction, and this existence of circumstellar disks is just the prediction we need. If this theory of star formation is correct, then there should be flat disks of material surrounding young stars. So what evidence do we have that these things actually exist in nature? So sort of the original piece of evidence is related to the spectrum of these stars. So if you look at a young star, it has not just the typical black body curve that you would expect for a star, but it has this extra bump of material towards long wavelengths. So remember, all black bodies emit spectra like this, and the peak of the black body's emission, the wavelength of the peak, depends on its temperature. So a star will be very hot, and it'll have a peak towards short wavelengths. So the protostar is emitting light at very short wavelengths. And this bump is a bunch of extra material that's emitting in the infrared. So it points to cooler material close to the star. So it's in the same region as the star. You know, we point our telescope at this young star and we get both of these, we get all of this emission when we look at it. So we're getting this peak, this black body peak, and this cooler infrared material at the same time. So here's some real data that just shows that. These are a bunch of young stars, and the points in these cases are the real data. And you see that they have this black body peak from the star, and then they have a less intense, longer wavelength peak of excess emission that we call infrared excess. Not very creative, but that's what it is. So it points to material that's warm, but not quite as warm as the star, radiating in very close by to the star. So this is, in a way, indirect evidence of circumstellar disks. That's what we think is the cause of this infrared excess. These disks are being heated by the protostar, and they're glowing, albeit they're not glowing as hot as the star is. They're glowing at a longer wavelength because they're cooler. And we only see this around young stars. But we also have direct evidence that circumstellar disks exist. So this was the variety of evidence that we kind of started with when we first started looking for circumstellar disks, but as cameras got better and we were able to take higher resolution pictures, we can actually disentangle this and just get direct evidence. So on the left here, you see some images of very young protostars, and here you see this entire picture that I showed you before in a cartoon way being played out in reality. So this star on the upper left, HH30, is a classic example of a protostar. What you see is glowing material, and if you look, so the star is at the very center of that image, and to either side of it, you see kind of a dark lane, kind of like looking at the plane of the Milky Way. And that's the dusty material surrounding the star that you see. To the top and the bottom, you see material that's glowing, and that glowing material is not blocked by the dust in the disk surrounding the protostar. So the flat, dark lane that you see through the center is the disk, and that green line that you see extending from the star, that's the jet that I also showed in that picture. So those jets don't last forever, but the disks actually last for a considerably longer time. And on the right, you see some further evidence. So those 4 pictures on the left are all examples where you see that dark lane of material from the disk. And on the right, you see disks with different geometries. So these are disks in the Orion Nebula. So the background of the Orion Nebula is glowing red for reasons that we'll talk about later. And in the foreground, in between us and the nebula, you see some young stars that have this dark patch around them. So what's happening is the glowing background of the Orion Nebula is being absorbed by material in this disk. So the dust in the disk surrounding the star, which is the point at the very center, is absorbing background radiation from the Orion Nebula and preventing it from reaching our eyes. So in a way, what you're seeing is a shadow or a silhouette of the disk. So this is direct evidence that young stars have this material surrounding them. So young stars, all very young stars, are surrounded by gas and dust that we can see directly or indirectly through the infrared excess emission. And we call that gas and dust that surrounds them protoplanetary disks, or circumstellar disks, which is the word I used earlier. Protoplanetary can be used kind of interchangeably, but I like it because it's more evocative of planet formation, which is something we're going to talk about here in a minute. But first, let's finish talking about what happens to this material. So you might ask the question, based on what I've been telling you here, why don't all stars have protoplanetary or circumstellar disks around them? Why only young stars? And to understand that, we're going to have to go to some basic physics and talk about momentum. So momentum is a quantity that all different types of particles carry, including photons, which are massless particles. So the momentum of a photon is related to a universal constant called Planck's constant and wavelength. So it's Planck's constant over the wavelength is the momentum of a photon. So that means that momentum, which is represented by P in this equation, and wavelength, which is represented by lambda, are inversely related. So they're indirectly proportional. As lambda or the wavelength decreases, the momentum will increase. So long wavelength, low energy photons have low momentums and vice versa. For massive particles, momentum is related to their mass and their velocity. So for a given momentum, if the mass of a particle is small, its velocity will be large and vice versa. So what the takeaway there is that momentum is related to both mass and the velocity of a particle. So let's talk now about how these 2 different varieties of momentum can manifest themselves in a circumstellar disk. So here we have a disk surrounding a young star. So the protostar has just turned on and started to radiate, although it's not fusing yet in its course. It's not a real star, but it's radiating like a star. And surrounding it, you have this disk, this flat disk shown in blue here of material. And if we zoomed in on it, which is what this bottom picture is meant to represent, you'd see that it's composed of two different kinds of material. It has both molecules, so dust, solid particles, and gas, which are smaller particles. And in a circumstellar disk, the gas is much more numerous. The particles of gas are much more numerous than molecules are. In fact, at the beginning, when a protostar is born, the material surrounding it has a ratio of 100 to 1 gas to dust. So there are 100 gas particles for every molecule of dust. But the two are affected very differently by photons from the star. So let's consider what happens when a photon is absorbed by each type of particle. When a particle absorbs a photon, the momentum of the photon is transferred to the particle. But remember, the equations for the two are different, right? So a photon of light carries momentum according to its wavelength, and a massive particle will carry momentum according to its mass. So the difference in mass between the dust and the gas is going to have an effect on how each is affected by absorbing a photon. So if we look first at the dust, so this big molecule here, when it absorbs a photon of light, it has a big mass, so it'll have a small velocity. So the radiation that's absorbed, the photon, is going to transfer its momentum to the dust particle, and it'll give it a small velocity because of its big mass. But if the same thing happens to a dust particle, it's going to have a much bigger velocity because all of the momentum of the photon was transferred to it, and it has a smaller mass. So it has to have a bigger velocity. So what happens then, we call this phenomenon radiation pressure. So the radiation, the photons of light from the protostar are absorbed by material in the disk, and the momentum is transferred, and that big velocity means that the gas is going to be blown out of the disk much faster than the dust. So dust is one way to keep a disk around. It's something that sticks around for a long time, but even it was getting blown out. It was having momentum transferred to it from the photons from the protostar. So disks can't survive forever. This is why not all stars have circumstellar disks. Eventually, radiation pressure will blow all the material out of the disk, starting with the gas and then moving to the dust. So here's some evidence to support that idea. Disks don't live for a very long time. So what you see here is a plot with age along the x-axis and disk frequency along the y-axis. So this group that made this plot, they looked at every nearby star-forming region, and they counted up in these star-forming regions how many of the young stars in the region have disks around them. If it was 100%, it would lie at 100 on the y-axis. So as you can see is that as the age goes up, so as these clusters get older and older, you get fewer and fewer disks around them. So the idea is that these disks, they don't last very long. They last kind of on the order of 5 to 10 million years, which is not long in universal time, in astronomical time. So disks don't live very long, is the takeaway there. So the percentage of stars that show evidence of disks decreases rapidly with time, which means only very young stars have disks. And planets have at most 10 million years to get started. So these disks that I talked about before, at about 10 million years, and even at 5 million years, the disks themselves, they're not made up of very much gas, right? The gas got blown out of the system pretty quickly. And the evidence to support that idea is that when we look at these young stars, we see a lot of these things called debris disks, which are disks that don't have any gas left in them. They're disks, but they're disks that are composed only of dust. So here are just some examples of debris disk images that we've taken. And in all cases, the star, which was at the center, has been subtracted so that you can only see the disk. So these are real pictures to support this picture of star formation that you would create a protostar with a disk around it, and that the disk would be cleared of gas first. So the exciting thing about these debris disks is that in several situations we've actually detected planets in them. So on the upper left, for example, is the star Fomalhaut with its debris disk that you see there. And remember, the light from the star has been subtracted so that you could see faint things like the disk, and even fainter things like in the little inset there are two dots labeled 2004 and 2008, and those are a planet orbiting in that disk that has been detected. On the right, in Beta Pictoris, which is another naked eye star, you can see the disk, and then in the very center they've changed the contrast so that you can see this dot, this tiny faint dot there, which is the planet Beta Pictoris b orbiting that star, inside of the debris disk. On the bottom left is another case where they've changed the stretch so that you can see the planets B, C, and D around the star HR 8799. So these disks of material surrounding young stars are mostly exciting in the sense that these have to be what planets are formed out of. And if our solar system is any indication, planets have to form before all of the gas is gone in the disk, because gas is what makes up most of the mass of the giant planets, like Jupiter in our solar system. Only the very core of giant planets is made of solids. So one thing that astronomers like me do is we look at this material surrounding young stars for signs that planets might be forming in them. So we're still looking for evidence that that we understand planet formation in the sense that they must be formed out of this material in the disks surrounding young stars. So we look for things like spiral structures and asymmetries and gaps, and of course we look for planets in these disks to try and verify that our view of how planet formation happens is correct. And just to give you a little more information about what that picture of planet formation is, here's what we think about. So in these disks of material, there are all other processes at work. So it's not just radiation pressure blowing grains out of the system. Grains can also coagulate. So if two grains of dust happen to encounter one another, they can stick together and grow in size, which, remember, is going to give them more resistance to the momentum of photons that they absorb. So they're not going to move out very much whenever they absorb a photon, the bigger they are. So basically what happens is you have small dust grains becoming big dust grains, then pebbles, then boulders, then planetesimals, and then planets. So growing. And a planet in a disk exerts a gravitational influence on the material around it. So once you start this process, you can get to a point where its gravitational influence will keep increasing and increasing, and it will sweep up material around in its region of gravitational influence and clear out the disk. So you might start to see disks that have these sort of gaps where planets have formed and are clearing out the material in that gap as they orbit the protostar. So this is the rest of our picture of planet formation. So you have, or of star and planet formation. So you have your giant molecular cloud. A piece of that, a core, will start to collapse and under gravity and form a protostar. That protostar will be surrounded by a circumstellar disk and an outflow. I didn't talk too much about that because it's not that important in the context of planet formation, but that is another consequence of physics. Essentially, you have to shoot material out if you're going to have material falling onto the star. So it's a conservation of angular momentum problem as well. Those jets don't last very long because the disk doesn't last very long, and material from the disk doesn't accrete onto the star for its entire lifetime. So you have a disk that dissipates with time due to both the radiation from the central star and to planets forming within it. So in the very young stages of a planetary system, it might only be partially cleared. You'll have a debris disk. And remember, that doesn't have any gas left over. All the gas has been blown out of the system because of the radiation from the star. So the dust is coagulating and forming planets. Another thing about this picture of planet formation is what you need to do is you need to store this material in planets before the disk is dissipated. So you have to form planets very early on in the disk lifetime, otherwise you don't have any material left over. And in particular, you need to have gas left over in order to make giant planets, which I'll talk about in a minute. So as these things start to impact each other, these dust grains start to impact each other and form bigger and bigger bodies, heat is generated in that impact process. And something interesting happens to the composition of these bodies as they grow, which is a hot object, in a hot molten object, denser things will sink towards the center. So more massive elements like iron will sink to the center of an object, and the lighter materials like rock, silicates will be on the outside. So this is something called differentiation, and it's another verification of our theory of planet formation, that small dust grains must stick to each other and coagulate to form bigger things. If that's true, then the heat generated in this process should cause differentiation. It should cause denser elements to sink to the center. So another prediction of this theory of planet formation is that the types of materials that we find and their phase, meaning solid, liquid, or gas, should vary with distance from their protostar. So you could ask, where would you expect in the nebula surrounding our sun, the solar nebula or protosolar nebula, that you would have found things that were gases or liquids or solids? What does that depend on? So traditionally that depends on temperature, right? In regions where it's very warm, you tend to have gas. And in regions where it's a little cooler, you'll have liquids and then solids. So you could think about this in the context of water, right? In hot places, like if you boil water to a very hot temperature, it'll become water vapor. At slightly lower temperatures, it'll be a liquid. And at very low temperatures, it'll be a solid. So if it's warmest towards the star, you will have gas in the nebula closest to the star, and then liquids a little further out and solids a little further out from there. So in the context of forming planets, we often talk about something called the ice line or the snow line, which is this idea that there's a specific temperature, a specific distance in the nebula where you have temperature sufficient for liquid water and solid water. So the point when water will freeze out. So inside of this snow line, you're going to have rocky planetesimals, and outside you're going to have icy ones where water is no longer in vapor liquid form, it's in solid form and has frozen out onto the planetesimals. And that ends up being important in determining the types of planets that are formed. So we think that water is important both in that ice, when two bodies that are icy collide with one another, we think they have more of a tendency to stick together. And also it helps to build up the mass of the objects outside of the snow line. So you tend to have bigger protoplanets out there. So what this ends up doing is it creates three different types of planets in these disks. In the very inner disk, where the temperatures were too high for solid water, where water was in the gas phase or liquid phase, you have rocky planets. Just outside of the snow line, you have gas giants. And the reason you have these, I'll explain here in a minute, instead of ice giants, which are a little farther out. So these are the three types of planets. You have rocky planets, you have gas giants, which have an icy core and a gas envelope, and then you have ice giants, which are mostly just the icy core with a little envelope. So the idea here, the reason why you have both gas giants and ice giants outside of the snow line is because in a gas giant, what has happened is just outside of the amount of material is also going to vary in the disk. And just outside of the snow line, you have lots of material. You have a big icy core, and it's just, if your core is big enough, it'll sweep up the gas in the disk. So again, this is exactly why we were talking about needing the gas to still be around when you form planets. So if you want to form a gas giant planet like Jupiter, you can't have blown all the gas out of your system through angular momentum transfer from photons to particles of gas. So this has to happen pretty early on in the lifetime of a disk. The ice giants don't have as much gas available because water isn't the only chemical species that has an ice line. So the types of gas that compose Jupiter, things like ammonia, they have a point when they will also freeze out to become solids. And in the outer disk, where planets like Uranus and Neptune are in our solar system, the temperatures are so low that most species are ices. Very few of them are gas. So they tend to form ice giants instead of gas giants. There isn't very much gas available in the nebula at that distance to form very, very big planets like Jupiter. So what evidence is there to support this picture of solar system formation? Well, the first one is this thing called the Zodiacal light, which I think I mentioned in a previous lecture too. The Zodiacal light is the debris disk of our solar system. So it's dust grains that were generated by collisions in the asteroid belt and the Kuiper belt that permeates our solar system. So it's dust that permeates our solar system, reflecting starlight. So remember, in this picture, it's often confused with the Milky Way, but the Zodiacal light, first of all, it doesn't have dusty patches in it, and secondly, it's not in the same place as the Milky Way. It's along the ecliptic, or the path of our solar system. There's a diffuse light. So next time you're at a really dark site, go out and look for this. So it's interplanetary dust that causes the Zodiacal light. Here's just another picture of it. The other piece of evidence that we have is that we can actually take samples of bodies in our solar system. And when we look at them, we see that depending on the size of the object, you have differing degrees of differentiation, but it's present in all of them. And that's consistent with our picture of how grains coagulate and grow in these nebulae. Okay, so let me summarize here and bring this all together to talk a little bit more about the material between stars. So we call the stuff between stars the interstellar medium, and it's composed of two types of things. You have gas in various forms. It can be cold, it can be hot, it can be ionized or neutral, and then you have dust, you have solid. So both of these things make up the interstellar medium. So here's a picture of our galaxy in hydrogen 1, so neutral hydrogen. So in an emission line of neutral hydrogen, a radio emission line, if we look at the galaxy, we can see that the plane of our galaxy is completely permeated with neutral hydrogen. We also know that there's lots of dust. So the dust in the plane of the Milky Way, in these Bok globules, we see it in other galaxies too. So on the upper right here is a picture of a galaxy with a big dark dust lane running right through the center. The idea here is just that dust is kind of ubiquitous in galaxies. It's everywhere. What's a little rarer is ionized hydrogen. So this is where these H2 regions we were talking about before came in. When these protostars become stars and they start radiating lots of light, they'll ionize that neutral hydrogen gas that permeates the galaxy. So regions where stars have just formed and there's lots of gas available because the giant molecular cloud hasn't quite dissipated yet, you'll get lots of glowing emission from ionized hydrogen. So if we look at the galaxy not in neutral hydrogen, which is the top picture, but in ionized hydrogen, you can see that there's a lot of structure here. Star formation is happening in lots of places in the galaxy, but they're very localized, right? There are little patches along the galaxy where stars are forming. As these stars form, so here's a very famous picture called the Pillars of Creation, which is in a star-forming region called the Eagle Nebula. And what you see in each of these pillars at the very tip is this sort of glowing cloud of dust. So what's happened is a protostar has just formed in the core there, and it's starting to blow away the gas and dust. So this stuff is dissipated with time. One good thing about the universe creating all different types of stars is that the birth of massive stars, not only does it create these heavy elements that are so important to the formation of planets and life, but they dissipate it into the galaxy in the massive shock wave that's emanated from a supernova that carries away the heavy elements that are created in the supernova, and it also will plow into material elsewhere in the cloud. So remember, those young stars, they don't live very long. So if a massive star is created at the tip of one of these pillars in the Eagle Nebula here, it'll die in a few 100 million years before the rest of the nebula has dissipated. And what happens there, so, if you have a supernova explosion and you have some nebular material left over, the shock wave will compress it and it'll start a new wave of star formation. So supernovae are very important in sort of the cyclical nature of this process, right? Stars are born, they die, some of them die in supernovae, but supernovae actually, they enrich the interstellar medium with heavy elements and they can trigger new episodes of star formation. So there's sort of a death and birth thing going on there. So this material, as young stars are formed, will end up getting dissipated, and eventually you'll get something like the Pleiades. So here's a picture of the Pleiades, which many of you saw at our star party last week. And if you were able to take a high-resolution picture of the Pleiades, you'd see that it's not just stars there, but there's this kind of hazy blue material surrounding it. That's sort of the very remnants of dust that were left over from the molecular cloud. All of the gas has been blown out of the system, but because momentum transfer doesn't happen as efficiently with heavy particles like dust, it'll take longer for it to be blown away. And so in very young star clusters, all of these are main sequence stars, so they've gotten out of the protostar phase, they've started fusing in their cores to be a real star, they're in hydrostatic equilibrium. But there's still a remnant of the material that they were formed from there. And that won't last forever either. Massive star clusters like this, so since giant molecular clouds are very massive, they have enough material to create hundreds or thousands of protostars. Once those stars form, they'll start behaving as stars do. They'll start interacting gravitationally with one another. And eventually this cluster will be dispersed because of gravitational influences. So they'll start to churn around and stars will get flung out of it because of the influence of other stars. So here's just a summary of what I talked about today. On the left, you have this pictorial representation of the process of star formation. Throughout the galaxy, there are these giant molecular clouds, which are cool and dense, and in these clouds, something might happen, something like a supernova, to cause them to start to collapse. The very densest cores will collapse to form protostars. The energy that's generated in the collapse process will be released in the form of radiation. The material that's left in the region surrounding this protostar, as the cloud spins, will flatten into a circumstellar disk. The material in this disk the dust grains in the disk will start to collide with one another and grow to form pebbles and then boulders and planetesimals and then planets. The planets will, as they orbit the protostar, start to sweep up the material around them. They have to begin this process before all the gas is gone from the disk so that you can form massive planets like Jupiter. So generally the material between the stars, the interstellar medium, has a variety of different phases. You have these cool dark cores, the giant molecular clouds. You have lots of neutral hydrogen everywhere in the galaxy. Once stars are formed and they start emitting radiation, they'll ionize this neutral hydrogen, and these star-forming regions will happen at just specific places in the galaxy where the giant molecular clouds have collapsed and formed young stars to ionize the neutral hydrogen that's present everywhere. These star-forming regions will form both low-mass and high-mass stars. The high-mass stars will die as supernovae, very early on after the birth of the stars in this cluster, and the shock waves will plow out into the interstellar medium. They'll cause pieces of it to collapse and form new stars. And the material that's left over between the stars will be slowly dispersed till eventually you can't even tell that stars were formed in this particular region. So there's a cyclical nature to this process of stellar birth and death. And there's a lot of evidence to support the theories that we have of star and planet formation. I showed you lots of images of various stages in this process. So we think we have a very good understanding of how this works, and we accumulate evidence to back it up all the time. So next time, Maria is going to summarize the unit by talking about what happens in systems where there's more than one star. You can have lots of exotic things happen, and this will serve as kind of a summary of everything that you guys have learned about in this unit.